Hello everyone again, and welcome to the continuation of our GeoTalk series. So today it's my pleasure to introduce Niall Groome. So Niall is a PhD student working at the School of Earth and Environmental Sciences in Cardiff University. And today he's going to talk to us about his ongoing PhD research on the evolution of the geology, or the geological evolution of the Isle of Anglesey in North Wales. So Niall, I think now you can share your screen and we can start the presentation if you can.
Yes. Thanks, David, and thanks everyone for joining today. I wanted to basically go through the story of the history of Avalonia. Avalonia is essentially the beginnings of England and Wales. And a big part of the geological history of Britain is locked into this story. So, as I'm sure many of you have heard, the geology of Britain is pretty renowned as being very diverse for what is an incredibly small area. And this story has a big role in that. And so we're going to essentially go through the history of the beginnings of England and Wales and how they went from basically one side of the earth to the other to collide with Scotland and form not the British Isles as we know them today, but to lay the framework for that story. So just to familiarize you all with the terrains that we have. So in Scotland, we have the Laurentian terrains. So Laurentia is a continent which sat roughly at the equator. It's mostly made up of North America, essentially, but with parts of Scotland as well. Then we have to the south, Avalonia, and Avalonia is what we're going to focus on today. It comprises most of England and Wales. You can see this yellow patch towards the base of Wales and across southern England. That's the Variscan front, which kind of obscures the lower half of the Avalonian terrain, but Avalonia basically covers most of the southern half of the UK, and it's split into these individual terrains as well. And one kind of important feature is this little sliver in the middle, including Anglesey here, a little bit of Llyn Peninsula on mainland Wales, and down here in southeast Ireland as well, in Brosleigh. And that gives us an important part of the story as to how we kind of reassemble what has happened in the past here. So the beginnings of the story, we start about 600 or 700 million years ago to set the scene. Earth is split into essentially four main continental land masses. So we have Laurentia, as I've already mentioned, up near the equator, and you can see this little patch here is Scotland and a little bit of Northern Ireland as well. So if there's any Irish people in the audiences, I'm not going to talk too much about Ireland, but it essentially goes through the same process where we have the northern half of Ireland and the southern half of Ireland coming together in the same way that Scotland and England and Wales come together. In the south, along the South Pole, we have the continent of Gondwana. So Gondwana is it's a very large landmass made up of Africa, South America, Australia, Antarctica, India. So a large area which covers a large span across the South Pole. Then we have, on the outskirts, we have Baltica, which makes up parts of Northern Europe, and Siberia as well, which we will kind of mention a little bit, but they're not going to be too important. The main focus will be on Laurentia and Gondwana and what's happening on the margin of Gondwana here. So you can see these yellow patches, these represent Avalonia, and Avalonia is what we're going to be focusing on as it makes its way from here in Gondwana up through to Laurentia. And they are separated by the Iapetus Ocean, which is a large ocean in between the two land masses. It's opening roughly north-south, and by this point, it has started to subduct beneath both land masses. And so roughly our first episode of volcanism that we have in Avalonia occurs about 677 million years ago in the Malverns in central England. And this is the first hint that we have subduction of the Iapetus Ocean beneath Gondwana and what will eventually become Avalonia. And we get this first hint of magmatism. It's calc-alkaline, kind of granitic to intermediate volcanism, with an affinity for magmatic arcs. So by using the geochemistry of these volcanics, we can kind of determine where we'd expect that they formed from. And for these early episodes of volcanism, we have an arc signature, which suggests that we have subduction of oceanic material, which is forming on magmas beneath the continental crust. And we're getting arc-related magmatism as a result of that. And a major episode of this calc-alkaline arc magmatism occurs across England and Wales about 620 to 580 million years ago, which is when subduction really seems to start ramping up. And so we can see that during the Precambrian, towards the end of the Precambrian, we have we have a large episode of we have large-scale subduction, and this would have occurred across not only England but the Avalonian terrain and other arc terrains across the margin of Gondwana would have occurred across probably thousands of kilometers. And we'll see a bit more of that in a moment. So we then have a second late episode of magmatism, or a third if you like. It occurs in the Wrecking terrain. So again, Western England, central Wales. And this magmatism is not so arc related, but it has an affinity more for rifting margins. So it seems to suggest, so this late episode of magmatism seems to suggest a switch from purely subduction related activity on the margin of Gondwana to almost a rift setting. So we have this major change around the Precambrian to Cambrian boundary from subduction related processes mostly to an episode of rifting. And along the margin of Avalonia, again, we have this this terrain, this Rossler-Monaine terrain, including Anglesey, where we can actually see that oceanic material has been accreted along the margins around 550 million years ago. And that is a rare episode of direct evidence that we have subduction of the Iaptus Ocean. And it's also seen, this is probably one of the only places that this is observed, other than another part in Hungary and Western Germany in the Bohemia region, which occurs a little bit later than this. So the record of subduction that we have in Anglesey, we have two main methods of recognizing this. So the first is using this blue unit here. So this is a map of Anglesey. We're in Northwest Wales at the moment. So this unit here is a blue schist unit which formed around 550 million years ago. And you can see it in the field. It's not particularly exciting in the field or particularly blue, but in thin section we can see this really nice blue coloration. This is a mineral called glaucofen. And glaucofen is a species of amphibole. Amphibole is a pretty complex mineral with lots of different species related to subtle chemical changes which reflect their environment. Basically, they're very sensitive to environmental changes, and in this case, those environmental changes would be pressure and temperature. So glaucofen is renowned for forming at high pressure and low temperature environments, which you only really find in subduction zones, where you have cold oceanic crust subducting beneath continental material. And because it remains cold and is quite thick slabs, it doesn't heat up at the same temperature as a normal geotherm. So it can get to pretty high pressures pretty quickly without actually heating up that much relatively. And that's how we get this unique formation, which is direct evidence of subduction. And another way that we have identified subduction is through this unit here, this green unit, known as the Gunnar group, where we have basically a record of the Iaptus Ocean and its life cycle, essentially. So you can see here a cross section of an ocean floor. So at the starting point here on mid-ocean ridge, this would be kind of the opening of the Iaptus in the center, where we have our pillar basalts and other kind of basaltic volcanic rocks, which spew out into the bottom of the ocean and kind of make the basal layer of our ocean. And young hot oceanic lithosphere is relatively buoyant, and so we kind of get relatively shallow depths, not very shallow, but relatively shallow, and so we can start forming sediments which form at, again, relatively shallow depths, which is what we see on Anglesey in this record here. So we start forming carbonate rocks along this margin here, and then as we go into deeper environments along the sea floor, we have deep sea floor sediments such as cherts, which form, and there's possible evidence of accreted seamounts in there as well. And as we move towards a continental landmass, so we know our Iaptus Ocean is subducting beneath a continental landmass. So our ocean floor is moving towards the continent, and as we get closer, we're going to get more and more sediment input being washed off of the continent into the ocean and accumulating on the seafloor. And that's what we see as we start to accumulate silts and sandstones. And then as we get to this zone here, where we have collision with the continent, we get an overprint of deformed material, essentially. And that's exactly what we see in this unit on Anglesey. And we can form this nice column of it. It's rare that we're able to do this. Most of the time, subduction has essentially ruined this, and the assemblages are largely chaotic. But in rare occasions, we can actually observe this stratigraphy. And along with geochemical analysis of the basalts, which again has the affinity of this mid-ocean ridge signature, we can then pretty confidently claim that we have accreted material from an ocean floor. And so if we move on to the rifting of Avalonia away from Gondwana. So we mentioned before how our volcanics shifted from arc-related volcanism, pretty similar to what you may have got in the Andes in modern day setting. We have this long ridge of this long chain of volcanics down the margin of the continent. Now we've started to get into a rifting phase. And Avalonia, along with other terrains as well, so terrains like Cadomia, for example, which are pretty similar to Avalonia, but they just occur spatially further away. They start to rift northwards. But we need to have a mechanism for this rifting to begin. And so the most likely mechanism that we have for this is if we subduct a mid-ocean ridge. So by subducting the mid-ocean ridge, you're bringing in a component which is actively causing rifting. And it appears, based on the differences in ages between our volcanism along the margin of Gondwana. So over here in Western Avalonia, which is modern day Canada, the volcanic trend is about 30 to 40 million years ahead of that in the UK. And the UK is similarly ahead of those in mainland Europe, so Spain and Bohemia, for example. So we have this kind of systematic unzipping of the margin of Gondwana, starting with Western Avalonia and traveling along through to Cadomia. And so we think that the best way to explain this is if we have the oblique subduction of a mid-ocean ridge, pretty similar to modern day California. So we have the Pacific rise, which is being subducted, well, was subducted during the Cenozoic beneath Western United States. And we can see that it's kind of opened up the Gulf of California here, it's separated off this strand of Baja California, and then we have the Californian basin in here as well, and associated volcanics as we see in Avalonia. So this is probably a pretty similar example. I don't think models would support this either, that this subduction zone actually has the legs for Baja California to eventually become separated as Avalonia was. But it's a pretty good analog for what the cause may have looked like. And another important feature of it as well is that this model also helps to explain the the high presence of transcurrent faulting along Avalonia. So obviously, one of the most famous faults in the world, the San Andreas fault, is a transcurrent fault, which is caused by this oblique subduction of a mid-ocean ridge. So mid-ocean ridge is a kind of segments of extension bound by these transcurrent faults. And when in domains where these transcurrent faults take over, as we can see in the San Andreas fault, you can get pretty large areas of transcurrent movement along the margins of this continent, and it explains a lot of what we see across Wales and specifically on Anglesey, where we have just a bit more outcrop basically, and we can see this a bit better. So in Anglesey, we essentially have our outward terrain of accreted material against the margin of what is supposedly the arc, the volcanic arc boundary along this line here. But that can't explain how we have this lump of granite in the middle, essentially. So what it looks like is happening is that we have these transcurrent fault movements along these northeast-southwest corridors. And if we have oblique subduction of an oceanic crust, we can have our accretionary complex forming as the ocean is being subducted beneath it. But we also have a vector moving in a transcurrent direction as well. So if we take a slice through this randomly, as Anglesey essentially is being a small island, then we can get occurrences where arc material has just been slipped in front of some accretionary material, and that's what it looks like has happened on Anglesey. And it would explain a lot of, well, it goes into the account of having this staggered rifting essentially as the mid-ocean ridge is subducted slowly, piece by piece, along the margin of Gondwana. So as we rift away from Gondwana, we essentially form a volcanic arc going through kind of Cambrian to Ordovician period, where we have our arc front along this line here. Our volcanic centers will become essentially Snowdonia in this area, and also in St. David's in Pembrokeshire as well in the south. Again, we have material again still being stacked up in front of the arc here. And we've also opened the Welsh Basin which cuts across Anglesey. And now we can get a much better record of what's going on, because we have a lot of strata, and we're in a period where we have quite noticeable fossils as well now. So trilobites and graptolites, for example, provide a really good record of how this basin is evolving during this rift episode, as the Avalonian arc is pushing forward across the Iapetus Ocean, and the Iapetus Ocean is subsequently closing. And so we kind of push north as the Iapetus Ocean begins to close. In the background, we have the Rheic Ocean opening. So the Rheic Ocean will open between our Avalonian arcs and our other arcs, which are slowly becoming unzipped from Gondwana as well, and following in the same direction. And then we're essentially replacing the Iapetus Ocean with the Rheic Ocean. and moving these arcs northwards towards Laurentia. And at the same time, Baltica is also migrating that way as well. So the model of how this actually happens is maybe a little more complicated than it seems. So whereas the logical progression would be a straight path, there's also this other theory which has been widely kind of pressed recently, which suggests that rather than a straight path, we actually have a curved path. So the oblique subduction of our Iapetus Ocean is actually driving transcurrent movement around to cause the rotation of our arc material as opposed to just a straight line path. So the problem with this is that it requires the rotation of the arc material, which doesn't necessarily fit with what we see on Anglesey. So on Anglesey, in those sequences that I showed you before, we have our sequence of the Iapetus Ocean as it has been preserved. So we start with our basalts, and then our sediments are laid down on top. And it's a pretty good way up indicator. So we can tell in which direction these sequences have been accreted, and they've all been accreted essentially facing towards Avalonia, which would make sense because we assume that it's an Avalonian margin. It's not necessarily an Avalonian margin. There's been a case made that it's a margin of a different arc, but the evidence seems to suggest that we do have that we are at the margin of an Avalonian arc, and the fact that we have our imbricated sequences pointing towards Avalonia, as they would have been kind of pushed into. So they would have been pushed towards Avalonia, and they would dip towards the continent that they were accreted against. And that's exactly what we see in the case of Avalonia. Whereas if they had been rotated in any way, then they would face the opposite way. And maybe not the opposite way of Avalonia, but certainly the opposite way of Gondwana, which we don't see. So a traditional kind of linear path is more suitable in this case. And so we get towards the end of our story now. We have our collision, essentially. So first of all, Avalonia would collide with Baltica about 440 million years ago, as both kind of approach the margin of Laurentia. And there's not too much evidence of that from the aspect of the UK. But moving forward, Avalonia then, with Baltica even, then collides with Laurentia. And this is the moment where we have the binding of Scotland, England, and Wales, and Ireland as well. As these come together. And then we have our other arcs as well, which have been stripped from Gondwana, which kind of come in behind. So we have likes of Cadomia, which binds just below Avalonia and runs across Northern Europe, for example, which has essentially followed the same path, but just at a staggered, it's basically a staggered event. And this collision causes the Caledonian orogeny, as you can see here in red, which affects large portions of the eastern North America, Scandinavia, and up through Scotland as well to create Scottish Highlands. In a more local scale, we have the Acadian orogeny, which affects, which causes the Welsh Basin to be inverted and brought towards the surface, which is why we essentially see it today. And then just to round things off to where we are now, essentially, eventually Gondwana migrates north from the South Pole as well, and the Arctic Ocean closes. And around 335 million years ago, all the continents come together to form Pangaea. And then we have a collision, which causes the Riskin orogeny, which, as I mentioned earlier, kind of obscures a lot of southern England in terms of the geology and the relationship between Avalonia and Cadomia, but occurs again across Europe and across eastern North America. And then eventually we have the split of the Atlantic Ocean, which kind of brings us essentially to where we are today, roughly. So as David mentioned, I'll be around for questions afterwards. If you have any questions or want to get in touch for any reason, my contact details are at the bottom here. So thanks for listening.
Thanks a lot, Niall, for that interesting talk about the continental yo-yo, or kind of really long-term tectonic history of the UK. Really a long story back in time. So I'm really happy to take any question. That was a slightly longer presentation than usual, but I think, you know, if people are still want to stay a little bit, I'm sure we can take a few questions. Please just use the chat option, and then I can read them out for you. Comment from Jill saying, thank you.
Thank you.
It sometimes takes a few minutes until the questions come in.
That's fine with me.
So another comment, well, basically a thank you. It was useful to help understand this complex history.
Yeah, it's it is pretty complex, and it's pretty tricky to fit it into 20 minutes, which I obviously didn't do.
That's all right. I guess we've been through all the different phases. So perhaps I can ask a general question then.
Sure.
These rocks that we see in North Wales in the area of Anglesey, are they kind of really common rocks, or are they kind of special rocks that are kind of rare and not easily accessible in other places in the world?
Yeah, so they're essentially well, fragments of the seafloor which are preserved in very dynamic processes. So preserving them is very difficult, especially from such an age. So if we take blue schists, for example, then the vast majority of blue schists will not be older than Mesozoic ages, so 250 million years. These are over double that, so they're very rare, and they give us a really good insight into basically the processes between between oceanic and continental crust, which we don't really see recorded in the geological record that often. And it's very important in this situation, as I mentioned, because it's one of only 2 occurrences that we know of across the whole margin of Gondwana where we can actually observe this.
Cool. Yeah, there is a question, a series of questions actually coming through. So first question by Kevin Privet is about Cardiff, and is it not part of Avalonia?
Cardiff?
Yeah.
Yeah, I guess it would be. We don't see those kind of rocks in Cardiff. So in Cardiff, we have younger rocks, I think the Triassic in age. I don't really know a lot about the Cardiff geology. But the Triassic rocks, I believe, kind of sit on top what would have been part of Avalonia. But we don't have any evidence of Avalonian stuff in Cardiff. And as I said, because we have the Variscan orogeny, it kind of obscures what we can tell about the Avalonian geology in southern England and South Wales as well.
Yeah, so I think actually the question of Kevin was because in one of your map you had a boundary running along the coast in South Wales, and I think this is actually kind of related to a younger tectonic event, but Avalonia is older, and so that would probably technically be part of Avalonia.
Yeah, it would be the I think I can find it. It would be the Variscan margin. Yeah, so we have the Variscan front kind of obscuring basically the very edge of South Wales.
Yeah, all right, so thank you. Another question is from Alan Bowring. Are you able to suggest where the Steiner-Hunter complex on the England-Wales border fits in again? That's about 702 million years ago. That's a fairly technical question. Suspect Alan is a geologist.
Yeah, I'm just trying to remember which one it is.
And I'm not even sure actually I could place it on the map.
Yeah, I think it might be slightly out here actually. I think it's one of the, is it one of the locations which is just boreholes, I think. It would make part of the Fenland terrain, which we only know from boreholes, so we can't really say a lot about it other than it's there. So a lot of these kind of terrains which make up Avalonia are pretty poorly kind of correlated to each other, because we have such small amounts of outcrop that we can see for various reasons. Partly because there's not a lot of outcrop in central Wales and England anyway, because we have so much kind of glacial stuff on top of it and farmland essentially. And partly because we have plenty of other rocks which have been laid down on top of it since then. So we only have really fractions of what we know from the center of Avalonia. But yeah, given its age, it's probably, again, similar to the Malverns, but slightly earlier in terms of where we start to have some kind of arc magmatism occurring in kind of like an early stage, which is perhaps not as well documented as it might be, since there's only a few occurrences of it. Maybe it's more widespread and we just don't know about it. But I'd put it as part of a kind of early magmatism with the Charnwood terrain.
Okay, thank you. Yeah, apparently that complex is really well exposed close to Radnor. Apparently it's worth a visit according to Alan.
I'll check it out. I'll see if it's budget.
Yeah, thanks a lot. And then there is a third question by Edward. Have you researched these through fieldwork or studying the literature? If both, which has been the most productive? So I guess also a slightly associated question and a bit broader is, what is your research project about?
Yeah, so this was kind of a more broader topic for me to approach, just to kind of broaden my horizons as well as anything. So my focus is on the Isle of Anglesey and Clean Peninsula as well. So looking at the Precambrian to Cambrian rocks across Anglesey, which basically make up this accretionary complex and other units around it as well. So not working necessarily on the Avalonian rocks themselves, but on the rocks accumulated along the margins of Avalonia. So essentially looking to understand them, working a lot with the geochemistry behind them, which I didn't really want to get into too much today because it can get a bit heavy.
So which one, which part of your project did you enjoy more?
Probably the field work. I like to be out and about, and it's nice to go up to Anglesey and see some of this stuff. There's some spectacular rocks on Anglesey. It's a UNESCO World Geopark, and with good reason, because there are some great sites on there. So it's really nice to go up there. But obviously they both go hand in hand. If I didn't read up about it beforehand, I wouldn't know what I was looking at half the time. So both are pretty useful. Yeah,
great. Thank you, Niall. So yeah, it's totally worth a visit, actually, Anglesey, for the geology. And you can find a lot of information about interesting sites if you look at the Geomon UNESCO Geopark. And as you know, we also have a second geopark in Wales, which is quite fortunate. We've got two geoparks. The other one is Forest Fawr in South Wales. So yeah, we're quite fortunate. The geology in Wales is actually quite spectacular. And I think the rocks that Niall has been looking at are really special for our understanding of some fundamental tectonic processes in earth sciences. Early on during the study of these rocks, it was found actually that they were remnants of the ocean floor. And at the time that happened in the 70s, the research was published in Nature, which is a prestigious scientific journal, because that was a very interesting and groundbreaking discovery. And so for some reason, actually, these rocks are not very well visited, or there's not been a lot of follow-up studies since the 70s, which is kind of surprising because there are so many active research-led universities in the UK. But actually, these rocks are really special if you place them in their context, but also at the world level. There are some really, really unusual rocks there. So yeah, and Anglesey, as Niall said, is also a very lovely place to visit, at least when it's not raining. You get a lot of also interesting archaeological sites. So you can have a very interesting trip there, combining geology, archaeology, a bit of history, and if you're lucky, very nice, relaxing strolls on a sunny beach. So, so I guess that's all for this evening. I don't think there are other questions coming through. So I'd like to thank again Niall for his contribution today, and thank you all for coming. Next week, we're going to have the continuation of the GeoTalk series. We're going to talk about ancient volcanoes. Marc-Alban Millet from the school is going to tell us how we can use different scientific techniques to investigate the history of ancient volcanic environments, and I'm sure it's going to be again a very dynamic and enthusiastic talk. So thank you all for coming today, and I hope to see you soon, well, again next week. Bye.
Yeah, thanks everyone.